Okay, welcome back. And once again, hopefully what you did is you drew a picture. So f is some arbitrary function like this, and we're doing the integral from a to a. This is a confusing thing to do, from a to a. So what we're doing is, you start here at x equals a, and then you also end at x equals a. So you're sort of doing infinitely skinny rectangle. So this answer, the area under this curve, the width or the base of this shape, equals 0. The width of the shape is 0. So it doesn't matter what the height is. You're going to get, because the base is 0, this area is 0 no matter what. So this is a nice property. This integral is 0 no matter what f is. No matter what f is. Okay, so this one is kind of just by definition, like, no matter how you do the Riemann sum, you're always going to get an empty sum. That's always going to be 0. Okay, I'm going to do the rest for you, so I won't make you work for the rest. So here is one. The integral, property 3, number 3. The integral from a to b of f of x. So what does that look like? That is some graph like this, from a to b, doing this area under this curvy shape. That's what the definite integral means. The property is that this is equal to minus the integral from a to b of f of x dx. So the moral of the story is, if you flip the bounds, is the same as multiply by minus 1. And why is this true? This happens because, remember, when we're doing these Riemann sums, which are what define the integral, we take these delta x values, and delta x is always equal to b minus a divided by n. So it's the endpoint. So, okay, this is for integral from a to b of f of x dx. You take this interval and you cut it up into pieces, and you have these delta x values, which is the width of each individual rectangle, is how much the x value is changing. And if you're going from a to b, that's b minus a divided by n. And then for the integral from b to a of f of x dx, delta x equals minus, so the other way around, let's write it like this, a minus b divided by n. And because the delta x values get flipped around with a minus sign, that is what causes this minus sign in the end. So this is why is property 3 true. Why is property number 3 true? It has something to do with the definition of the delta x's in the Riemann sums. What is property 3? Property 3 is just saying this. You should definitely know property 3. We're not going to ask you why it's true, although, if you understand it, it means you're understanding what a Riemann sum is, and so on. Okay, that's property 3. Okay, what about number 4? Property number 4. And this one, we're doing the integral not from a to b, but from a to c. So here is some funny function, and we're doing the integral from a to c. And what we want to do is write it in terms of an integral involving some intermediate point, b. That's x equals b. And okay, so the integral from a to c is this whole area here, everything in here. And the point is, you can write that as a sum of two areas. You can write that as this as equal to the integral from a to b of f of x dx plus the integral from b to c of f of x dx. So the blue area, that's everything enclosed in here, is going to be the sum of this red area, everything in there, plus the yellow area in here. And that's just an obvious fact about the way areas add, right? The area of a big shape, if it's made of two smaller shapes, the area of the big shape is the sum of the two smaller shapes. Again, if you wanted to prove this, you would have to prove it using Riemann sums. It would be something about limits, and really will boil down to the fact that the limit of the sum of two things is equal to the sum of the two limits. That's really fundamentally what's going on here, because every time you write an integral, it's actually a limit. Okay, so one more time. That was like roughly why property 4 is true. You should definitely know property 4. Knowing why it's true is sort of bonus. Okay, that is properties 1, 2, 3, 4. Property number 5 is an inequality one. So if f is less than g, what does that look like? That means the f function is always above the g function. If f is less than g, what is true about their integrals? And so the integral from a to b of f of x dx, that is some area like this big blue area, everything under the curve over here. That's the integral of f. The integral of g is this little yellow area. And what's true about these areas? What can we say about them? Well, if f is bigger than g, then it turns out the obvious thing is that the area of f is also bigger than the area of g. Okay, I just realized I did this in reverse. So in my picture, I said f is bigger than g. F is bigger than g. But over here it says f is less than g. So I'm going to do a nasty, and I'm going to replace this. F of x is bigger than g of x. So if f is bigger than g, then the integral of f is bigger than the integral of g. Of course, the opposite is totally true as well. So if you want to write it down the other way, if f of x is less than g of x for all x in AB, then the integral of f of x dx is less than the integral of g of x dx. And these are definite integrals from a to b. Okay. Okay, so that, another intuitive thing, areas kind of respect height, right? If the height of one thing is taller than another thing, then the area of the first thing is also taller than the area of the second thing. Okay, the next one is multiplying by a constant. Okay, and just like everything else, you can prove it using limits. Okay, right? Why is it true? Well, limits also respect inequalities. That's why it's going to be true. Okay. Number 6, let's move on to number 6. Property number 6 says, what happens if you multiply by a constant? So let's pretend k is a positive constant. So this is, let's have some nice shape. Like here's f. Some funny shape like this. Here's f. And here is k times f. So it's the same graph of f, but stretched out by a factor of k. So it's like you take a big rolling pin, you take the graph of f, and you stretch it out by a factor of k. So what does it look like? Maybe something like that. Okay, let's do it in a different color. Let's do it in blue. This is the graph of k times x. K times f. So I took f and I stretched it out by a factor of k. That's what multiplying by k does. What happens to the areas? How is the area of the blue curve related to the area of the black curve? Well, if you stretched out the shape by a factor of k, you've also stretched out the area by a factor of k. So what does this mean? The integral of kf equals k times the integral of f. Simple. Okay, again, why is it true? This is like a true fact that you can see from areas. Why is it formally true? Mathematically, why is it true? The reason is because limits do the same thing. So you can write down what this is as a limit. You can write down what this thing is as a limit. And you can use the limit laws to show that they're equal. Okay. Property number 7. Property number 7. This is really two things. This is, one of them is the integral of f of x plus g of x. And one of them is the integral of f of x minus g of x. And when we have two statements like that, we combine them by using a plus minus sign to mean two symbols, two possible statements at once. So I'm going to do one of them as a picture. Let's do f plus g. So let's draw two graphs, and let's draw f plus g. So maybe f looks like this. Let's do that bump again. That was good. F. And let's say that g, yeah, this is a good one. Let's do g looks like this, right? Let's pretend g looks like that. This is g of x. This is f of x. What does f plus g of x look like? F plus g of x is you add them together, so it's going to look something like this. It's going to be two bumps. Two bumps. And, depending on how exactly the bumps are drawn, this will work out something like that. Okay, this is not, obviously, if you want to do it on a computer and do it precisely, you can do it. This is my cartoon of what's happening. So if f has one bump and g has another bump, you add them together, you get two bumps. So let's draw something like that. This is f of x plus g of x. Okay, and how are the two areas related? So what's the relationship between the area under the blue curve with the area under the yellow and the black curve? They add together. That's the obvious thing. So the area under the blue curve, f of x plus g of x, that's like the area of the two bumps. That's equal to the area under f plus the area under g. Okay, and once again, just like everything else, this fact just comes from limits. So if you know that limits obey adding, you can prove that that means these integrals obey adding too. So same thing for minus. So if you do f of x minus g of x, you get the integral of f of x dx minus the integral of g of x dx. And that's from a to b. Okay, those are properties of definite integrals. And I think they go with your intuition about what areas do, and they also come from the limit laws. Okay, those are those properties. There's one more page of things, and this page of things, these properties are like not as useful. Like these properties we've done, properties 1 to 7, These are not like everyday useful properties, but they are extremely useful in what we're doing next. So these properties come up in the proof of the next section, and that is why we have them here. And what I'm going to do is I'm going to fill them in when we need them. So I'm going to get them ready and fill them in when we need them. Okay, but these are the important properties you should absolutely know about definite integrals. All right, so we're going to stop there, and we're going to start 11.2 in the next video.